The Gnomon Workshop presents Dynamics 5 with Maya. Fields. With your host, Alex Alvarez.
Hi, I'm Alex Alvarez, and welcome to Dynamics 5. And this day we're going to be talking about fields. And in Maya, when you're dealing with either rigid bodies or particles, fields are a way to simulate natural phenomena or forces that exist in the real world, such as gravity or wind or turbulence. And so whether you're animating smoke or fire, animating a school of fish that you're doing via particles that you're using the instancer, whether you're animating a landslide, an explosion, whatever, fields are something that almost always are going to come into play. And so by having a thorough understanding of all the different attributes and the unique nature of each of those different fields, because there are several in Maya, that will give you the foundation upon which you'll be able to move forward to design effects. And that's what we'll be covering. Okay, so we're going to talk about the fields that Maya has. And if I just jump up this image, we can see that there are 9 different fields in Maya. And based on the icons that they have, you can get kind of not too good of an idea of what they do. Air, drag, gravity, Newton, radial, turbulence, vortex, and volume axis. There are relationships between some of the fields, but for the most part, all of these fields are unique. And so we're going to talk about them one by one. And for most of these fields, they do share attributes as well. And so for the attributes that they share, we're going to see them over and over again. So what we're going to want to do is, jumping into Maya, what I have up right now is a single omni emitter, which is emitting into 2 particle objects. And there are no fields in the scene right now. So the speed that the particles have is just the speed that they're getting from the emitter. So when you create a field, you can have either a particle object or a rigid body selected. If you have nothing selected, it will still create a field. It's just that field won't be connected to anything. So if I go in here and with nothing selected, in dynamics mode, go to fields, gravity, we will see that I get a gravity field in the scene, which I can move around, and in the outliner we will also see that there is a gravity field there. All fields have transform nodes, and they do not have shape nodes. So if you look in the outliner, you will not see a shape node listed. So if you look in the channel box, you'll see a bunch of transform node attributes, and then all of the field attributes. But since I had nothing selected when I created this gravity field, when I hit play, nothing has changed as far as this particle object and how it's behaving. If you want to connect the gravity field to the particle object after you've created the gravity field, I can simply go and open the Dynamic Relationships Editor under Window Relationship Editors, Dynamic Relationships. And in here I can select one or both of the particle objects and connect them to gravity by just clicking on the gravity field. So I'll click on the other particle object and select gravity. So now that I've made those links, if I go back to frame 1 and hit play, we will now see that the particles are falling with gravity, as you would expect. So something like the gravity field, which is the field we're going to begin with, is a relatively straightforward field, as based on the names of the different fields that we looked at, it's one that you might, and if we just jump this back up, be able to relate to, in the sense that pretty much everybody knows what gravity is. The other field in here that you would see and maybe understand is the one called air, although that's not too specific as far as what it does. And so going back into Maya, the gravity field is a field that pulls things in a single direction. It's actually almost identical to the other field, which is called uniform. So under the field pull-down menu, we can see the third one from the top is gravity, and then down here we have uniform. Both of these fields will push things in a uniform direction. It does not have to be down. And so if I select the gravity field and we look at some of the attributes that it has, underneath the transform node attributes, you'll see that you have magnitude and then a bunch of attributes. Magnitude is something that all fields have, and it can be either positive or negative. For the gravity field, by default, it has a value of 9.8. So if I change that so that the magnitude has a value of 50, obviously the particles are going to fall faster. But if I give it a value of negative 20, now they're going to move up instead of down. So just because it's called gravity does not mean that particles need to move down. And so because of some of the things that we can change in our fields, we'll see that we'll be able to get a gravity field to behave exactly the same as a uniform field. Because if I go in here and delete this gravity field, select my particle objects, create a uniform field, and make a couple quick changes to the settings on this uniform field, what you're going to see when I go back and I hit play is that we basically have a gravity field. And so I'm just changing its magnitude on this uniform field so that now it has a value of, let's say, 20. Or I'll give it a value of negative 20, and now they're going to go up. And so what we're going to want to do now is let's get a gravity field back. So I'm selecting both of the fields, or rather both of the particle objects, creating a gravity field. If I go to the creation dialog box, all of the fields obviously will have a creation dialog box with a bunch of different settings. But the thing is that everything that is in the creation dialog box can be changed later after you've created the field. And so there's no need to make any changes right now, fearing that you won't be able to change your mind. So what I'm going to do is just have the default settings. And what we will see is that looking in here, it'll ask you for a name, but you do not need to specify a name for any of the fields, as it'll just give it a default name if you don't. Then we'll see we have magnitude, which we just talked about, and then attenuation. All fields also have attenuation, which is a fall off or a drop off. Decay, which gravity does not have by default. So if you think of lights in Maya, all lights by default are created with a decay set to no decay, meaning the light goes into the scene forever. So it's the same idea. So with a gravity field having an attenuation of 0 makes it behave more like what gravity will do in the real world. Then for the gravity field, you'll see you have X, Y, and Z direction. By default, for a gravity field, the Y direction is set to -1. And that's why when you create a gravity field, it pulls things down or into the negative Y direction. Then we'll see we have an attribute called use max distance. If you think of a light again, something like a spotlight has something called decay regions, where you could specify in units how far away from the light's intensity diminishes to 0. It's the same thing with fields and their magnitude. So by default, gravity has use max distance off, meaning that if you turn off max distance and have an attenuation of 0, it means that that field exists in your entire world space. If you turn on your use max distance, you can then specify a distance in units. So if I enter in here a value of 25 units, that would just mean that 25 units away from this gravity field, it no longer will be affecting particles. Underneath the use max distance, we then have volume settings, which are all off by default. Volumes for all fields allow you to specify a primitive shape, like a cube or a cone or a sphere, and then the field will only exist within that shape or outside of that shape. So we'll talk about and do examples for all of these different things. So first, just hitting reset and having the two particle objects selected, I hit create. The particles will fall with gravity. Then with the gravity field selected, we've already changed magnitude. So let's see what happens if I make a couple other changes. If I move the gravity field, nothing changes as far as the particles because the attenuation is at 0 and the max distance is off. Obviously, if I turn on the max distance, things could start to change. In the channel box, you will see the attribute called use max distance is off. And then there's another attribute called max distance, which has a value of -1. If I turn on use max distance, and then I raise the max distance value to, let's say, 10, which means 10 units. If I go back to frame 1 and hit play, my gravity is not affecting particles until they get close to the gravity field, at which point they'll start to fall. So let's say I increase the max distance to 20 units. Now we can start to see that some of the particles are falling with gravity, the ones that are closer to the gravity field. So these attributes are pretty easy. But before we can then move on and see what attenuation means, because in this particle example it'll be a little bit difficult to see, let's jump down to some of the other attributes. So we've seen magnitude, max distance, and use max distance. We also have the direction settings. Right now direction at Y is set to -1. Let's set that to 0 and set it to -1 in X, and then increase our max distance to 50 units. Now when I hit play, the particles start to move in the -X direction. All right, so to create another example that's going to make it a little bit easier to see what these attributes mean, I'm going to open up a particle grid. And so with this particle grid that was created with the particle tool, if I select these particles, right now if I hit play, there's no fields. If I create a gravity field, they clearly will just fall down. And so we can see them all move in the negative y direction. So if I select the gravity field and enter a value of 1 for x and 0 for direction y, they move in the x direction. Now if I go and move the gravity field to the origin, to the center of all these particles, and enter and turn on use max distance, and enter a max distance setting of 10 units, and hit play, hopefully that is pretty straightforward of what max distance is doing. And then if I enter, let's say, a max distance of 5 units, and keyframe this field moving, and so I put it to the left, set a key, move it to the right, set a key a few frames later, and hit play, you'll see how that max distance combined with the translation animation on that gravity field has created this result. So other attributes we now want to look at, aside from our max distance, is I'm going to increase the max distance, let's say, to 25 units. So when I hit play, it's affecting practically all the particles. But then I'm going to turn on attenuation. And let's set the particles to move in the negative y direction. So I'll put direction y to negative 1 and direction x to 0. When I hit play, we get this. Well, if I enter a value of 1 for attenuation and hit play, we will now see this. So notice that the effect of the gravity field is strongest near the gravity field. Again, very straightforward as far as the behavior that we are getting. So at this point, now that you've seen attenuation, right now it has a value of 1. It can have a value of 0, a value of 5. It's up to you. The greater the attenuation, the greater the fall off will be from the location of the field to its max distance. So if I enter a value of 0, again we got this, while a value of 0.25 will give us this, where we can see that there still is that attenuation. It's just diminished by quite a bit. Now one thing I need to point out is, let's say we put the max distance to 5 units, turn on the attenuation and hit play. Notice that the particles continue to fall forever. But at this point, these particles down here are clearly outside of the max distance of that gravity field. The reason they continue to fall is because the particles conserve attribute is on. Always keep in mind that particles, all particle objects, have a conserve attribute, which by default has a value of 1, which means that they conserve energy or conserve momentum. So if it has a value of 1, even if that gravity field turns off, they'll keep moving. But if I put conserve to a value of 0 and I hit play, we will see a much more diminished effect. And what I'm going to do is I'm going to keyframe that gravity field moving again. So I'm going to select the field, set a keyframe on it, on its translate x, and then I'm going to move it down here and set another keyframe a few frames later. Now when I hit play, I'm also going to increase its magnitude to a value of 50. And what we're seeing, and let's try a value of 200 and hit play again. What happens is it hits those particles, and actually at frame 0, let's move that field back a little bit and reset the key on its translate x. When I hit play, you can now see what happens to those particles. That since the conserve is set to 0, once they exit that max distance range for the gravity field, they immediately stop. Let's put the magnitude up to 400 so that it's even more pronounced. They move and then immediately stop. If I take the particles and raise the conserve to a value of 0.75, what you will see is that they won't stop immediately, they'll just slow down. So notice that instead of stopping immediately, we get this result. So a value of 0, they will stop. A value of 1, they'll move forever. And then anywhere in between, you can control how those particles lose energy and slow down. So with these attributes set on the gravity field, when I select that field again, we now should understand magnitude, attenuation, and max distance. And we're going to be using these attributes again and again on all the different fields. Then there are attributes in here, as I've mentioned, that are called volumes. And we can see that we have volume, shape, exclusion, offset, and so forth. If I go back to frame 1, by default, fields do not have volume shape on. And so the only way you can control where in the scene they affect your particles is by either selecting the gravity field and moving it, or by setting its max distance? Well, instead of going and using the max distance, let's say I turn max distance off. When I hit play, we'll see that it's affecting all of the particles, but attenuation is still on. Well, now what I'm going to do is, with that gravity field selected, I'm going to go to volume shape and choose cube. You will see that a cube pops up around the gravity field. I can also select a sphere, a cylinder, a cone, a torus. Well, if I choose cube, what now will happen is if I scale my gravity field, that gravity field now only exists inside that cube. So if I hit play, we now see this. If I take the cube and I scale it non-proportionally, we see this. So that is a very intuitive way to understand how your fields are existing within your scene, so that you get some sort of visual feedback. And so you are allowed to non-proportionally scale, rotate, any of those kinds of changes will be respected. Also, I've mentioned that the field exists inside that shape. That's if the volume exclusion attribute is off, which is by default always off. Volume exclusion has to do with whether this field exists inside the volume or outside the volume. So when volume exclusion is off, it means that the field is inside the volume. But if I turn volume exclusion on and hit play, what we now see is the field is actually on the outside of that box. So something that you could do is if I had, let's say, a radial field. Radial fields can push things away or attract things. If this, let's say, was a sphere, and it was a proportionally scaled sphere, and it was a radial field, if I used a negative magnitude on the radial field so it attracted things, but turned on volume exclusion, I could have it so that we're safe inside the sphere, but anything that moves outside of the sphere gets pushed back into the sphere, if that makes sense. We'll see examples of this later on. So going back to some of these other attributes we have. Volume exclusion we just talked about. Then you have volume offset. If you change volume offset X, Y, or Z, you will see that we are basically moving where that volume is positioned in the scene. That's all it does. So if I increase our volume, let's say we go back to a cube, hit play, then I go to volume offset in Z, and offset a little bit in Z, and hit play. It's pretty obvious what that did. So it's up to you whether you use the offset attributes on that field, or you just manually move it. I prefer to just keyframe the movement of the field as opposed to relying on the offset attributes. We then have section radius and volume sweep. Section radius has to do with the torus shape. If I go to a torus, I can scale it, and this kind of looks like a donut, so I can scale that shape, but I can also go and grab the section radius to change what the radius is for the torus. Then if I go to volume sweep, that's going to change whether we have a full torus, a half torus, or whatever. So if we went to cylinder, obviously volume sweep will have an effect while the section radius will not. And so now we could have a pi wedge for our gravity field. So if I go in and let's say we choose a torus, and I get rid of the keyframes on the translate X, and I move this torus towards the center of my particle grid. Let's scale this up a little bit and maybe change the section radius. When I hit play, and let's increase that magnitude maybe to 4,000, so it's pretty strong. When I hit play, we can see the particles that move down are basically moving only in the shape of that torus. And I'll turn the attenuation off on that field just so that it's more obvious which particles moved away and which ones stayed behind. So another example in here of using something like the volume shape is if I go and open this example, I have some particles that are spelling out this word, and then I have this gravity field that is has a cube shape pushing particles in the negative z direction. And then I have another volume field behind the word, which is actually a turbulence volume. So if I hit play, we'll see that the gravity field, as it's keyframed to move throughout that word, pushes them back into the turbulence field, which then causes them to get ripped apart. And so it really is an intuitive way to design, motion of fields within your scene. Now, I've mentioned that a uniform field is just like a gravity field. Let's say we wanted to go and create the same exact effect. I could simply go in and delete my gravity field, select my particles, and now it'll create a uniform field. If you go to the options are exactly the same as the gravity field. The only difference is that instead of by default having attenuation off, a uniform field has attenuation on. And by default, instead of going in the negative y direction, it's going in the positive x direction. So what I'm going to do in here is set it so that the direction is going in the negative z direction. And I'm going to actually hit reset, hit create. Here's my volume field. I'm going to turn its volume shape to cube. I'm going to set its direction to be negative z, so that if I go and scale this cube a little bit and hit play, we'll see that it's pushing the particles in the middle. And so maybe I'll give it a stronger intensity. So I'm going to give it a magnitude, let's say, of 25. It'll push those a little bit faster. And then I'll simply scale it up a little bit more, move it down to the left of the G, switch to spline keys, and then I'll keyframe its X, move it through the word, and then after, let's say, about 60 frames, I'll keyframe it again. So that when we now hit play, what we're going to see is we get basically the exact same thing as we had before, just using a uniform field instead of a gravity field. So it's sort of up to you. I tend to rely on using gravity fields when I want gravity, meaning I just want things to fall down, just because I know the default settings will do that. But uniform fields I use more often than gravity fields, just because it's more of a mental thing as opposed to a necessity. You could really live without one or the other. And so if I have something where I have some crates that need to fall with gravity, I can simply go and select all these crates, which are active rigid bodies, and say, uniform field. And for this uniform field, have it go in the negative y direction. And if I go and hit play on this field and I give it a 0 attenuation, what will happen is it'll basically look like gravity. So that if I go in and tilt the ground a little bit and move it down so that those cubes will fall, when I hit play, it's a uniform field, not a gravity field, but it's really the same difference as far as the result that we're getting. And another example of using volume shapes with these particles is if I jump in here, I'm going to open a scene where we have some sort of fog. And so let me grab that in here. So there it is. We have a scene that has basically kind of a fog that could be existing in the scene. And if I hit play, we can basically see that the fog is kind of turbulent and moving around. It also could be just a mist or a ground fog or whatever. And so in order to get this fog, though, to stay in the scene correctly but be turbulent, if I went into the dynamic relationships editor and selected the particle object and deleted it from all the fields in the scene, it won't move. It's static. The fields I have in the scene are gravity, uniform, and turbulence. Well, if I connect the particle object to the turbulence and hit play, they're just going to scatter, and they're going to eventually just dissipate into the entire scene. They're not going to stay on the ground. So to keep them on the ground, I could then also connect them to gravity. But the thing is that they will now fall and continue to fall forever. So in order to get them to sort of stop on the ground, I could create a collision object for those particles, like a plane that they collide with. But the problem is then your mist will fall, hit the ground and bounce off of it, or hit the ground and suddenly stop. But what you actually want is you want it to, when it gets near the ground, to slow down and sort of be pushed back up a little bit. So for that I've used this uniform field. And so if I connect the particle object again to all of those fields, we can see that I have this uniform field, which is a cube, which is pushing the particles in positive y. It has attenuation, so that when I hit play, the particles kind of settle on it. It's almost like settling on a cushion of air, where they just settle on that uniform field that keeps them up, the gravity field keeps them down, and then the turbulence field allows them to still have that kind of behavior that can create a more dynamic result. So that's the basics of gravity fields and uniform fields. Actually, one more example that we can see real quick is if I, let's say, grab this one, where I'm using, let me switch to a different camera. I've got these ships that are sort of exiting from like a docking bay type of thing. And we'll see that as they exit, they speed up and then go in different directions. So if we come a little bit closer, notice that they're moving really slow when they exit. Then they speed up and then go in a different direction. Well, they're moving slow because the emitter that's emitting those ships, because those are instanced, emits them with a slow speed. But then once they exit the ship, they enter a volume uniform field, pushing them in the positive z direction. So that's what speeds them up. But they're only going to stay in that for about 10 units, at which point they enter a turbulence field in a volume, which then causes those ships to each go in a different direction. And so if I take that uniform field and give it a magnitude of, say, 50 instead of the 15 that it has right now and hit play, we're going to see that they're going to speed up and get a much higher rate of speed as they exit. And then they'll still enter that turbulence field that gets them to go and not all move perfectly straight. And so with that, you should understand the basic usefulness of gravity and uniform. What we'll now talk about is a vortex field. A vortex field is a spinning field. So what I'm going to do is I'm going to go to the particle tool, and I'm going to sketch some particles so that we have, let's say, something like a spiral galaxy. So I'm going to lower this radius in here, and then I'm just going to create what could be some different arms to this. And then I'm just going to hit enter. For this particle object, I'm going to make a couple quick changes. So I'm going to make it multi-point, turn on color accumulation, increase the radius inside there, give them some opacity so that they are not all opaque. And so I'll give them an opacity in here of 0.8, and then I'll also go to their color so that they, let's say, are all bluish. And so I'm going to go to their RGB PP and write a creation expression so that the RGB PP equals, and basically a RAND function between a minimum vector and a maximum vector. So when I hit create, if I go back to frame 1, we can see that they're kind of bluish. So the thing is that if I want to create something like a spiral galaxy, if I just rely on the particle tool, it's going to look very hand-drawn. And so I kind of need to spin this up. So if I select this particle object, I'm going to now go to the fields pull down and choose vortex. If I go to the options and hit reset, we have again magnitude and attenuation, and then we have axis. So axis is the unique attributes for a vortex field, and by default you can see that axis X and Z are 0 and axis Y is 1. So if I hit create, what's going to happen when I hit play is this. So you can see that that vortex field is going to spin the particles. And if I move the vortex field to the right and hit play, you can see that the location of the vortex field is where your axis is. So if I move it back to the origin, let's say I change it so that its axis, instead of being Y, I could change its axis to being X. So I'll enter a value of 1 for X. When I hit play, it now spins in a different direction. So what I'm going to do is get it back to axis Y. And now we have to figure out, well, how come if we wanted to do something like a spiral galaxy, we wouldn't necessarily want them to spread out like that. And the reason that they're spreading out is again based on the conserve attribute that the particles have. Because since the vortex field is a perfectly circular force, these particles at any given frame are trying to sort of move with a tangent to the arc that they're currently being pushed along. And so if I take the conserve attribute of the particles and enter any value other than 0, they'll try to spread out or spread away from the axis of the vortex field, as we're seeing. But if I enter a value of 0 for conserve, when I hit play, what we're going to see is the particles are going to move really slowly. And so now I'm going to select the vortex field and increase its magnitude. I'm going to give the vortex field a magnitude now of, let's say, 100. And now when I hit play, we see this. And now we're getting something that looks like a spiral galaxy. So if I stop playback at any moment, we can see what we've been able to do. And what we want to notice is that the middle is spinning faster than the ends of the tails. And that's because of attenuation. because by default the vortex field has attenuation on, meaning that the field's intensity is strongest at the location of the actual vortex field. So if I turned attenuation off for the vortex field and hit play and lower the magnitude down to a value of, let's say, 1, we see this. And let's increase it to a value of 5. So with the particles conserved set to 0, the attenuation set to 0, and the magnitude of the vortex field increased a little bit, we now have a perfectly spinning field. So let's put the attenuation up. Let's increase the magnitude to like 100. And then what we can do is hit play. And then once this looks the way we want it to look as far as something like a spiral galaxy, I can simply select the particles, save initial state on them, go back to frame 1, select my vortex field, and then turn off the attenuation and lower the magnitude back down to 5. So that when I now hit play, we have this. So let's lower the magnitude down to a value of 1, and now we have a spinning spiral galaxy, just like that. By using the attenuation to get the spiral look of the particle object to look more natural, save initial state, and then get rid of the attenuation, so now the particles are just spinning but not changing as far as their shape. And I could still apply any of the other fields in Maya to this particle object, but that gives you an idea of what a vortex field is doing and how the conserve attribute makes a very big difference to the result you end up getting with the vortex field. Okay. So another field that we want to look at is the drag field. And so what I'm going to do is, and also one thing I want to show you the vortex field real quick, is just remember that everything is keyable. Which I haven't really stressed yet. Not just the motion or position of the field, but also the axes that things are rotating around or moving or any of the custom attributes. So if I went in here and I turned the attenuation back on and put the magnitude back up so the field is strong, so that things are spinning again, I am allowed to go and keyframe any of these attributes. So if I went into the axis even and went to stepped keyframes and keyframe the axis at frame 1, and then change the axis of rotation to the x-axis at frame 150 and hit a key, what we're now going to see, once we hit frame 150, is that all of a sudden the axis of rotation completely changed. And so just an example of proving that everything is completely keyable within these attributes. So now to look at the drag field. I'm going to make a new scene. And the drag field is something that you can use to simulate air resistance or water resistance. And the fact that if you have smoke that's leaving, let's say, a smokestack, you have an industrial smokestack that is emitting smoke very quickly. What you will notice if you look in the real world at a smokestack like that is that the smoke might exit the smokestack moving really, really fast, but it then will lose its speed very quickly. Over the course of a second or half a second, it'll slow down and lose maybe 80% of its speed. That's because that steam, which is exiting the smokestack, hits the air, and the air resistance causes that steam to slow down. Well, Maya by default is a void. There is no air in the scene. So you have to recreate that by using a drag field. Another example is if you had you shot an arrow, like a bow and arrow. In the air, it's going to have one speed, but if that hit water, the moment that arrow enters the water, it slows down because water has a different density than the air does. So all of that can be recreated using drag fields that have volume shapes, for example, so that you could have under the water has a drag field that's a cubic volume, while above the water there's a different drag field that has a less of a magnitude than the underwater drag field does. So to see how the drag field works, if I create an emitter, so I'm going to create a, let's say, volume cylindrical emitter that's going to be emitting particles going along its axis. And so I'll hit create, and I'll set the settings so that along the axis we have emission. And let's scale this up a little bit and hit play. So that now I have particles that are rising with that emitter. And I'll also take these particles and switch them so that they look like spheres. And I'm also going to give them a lifespan so they live maybe 5 seconds. So that now when I hit play, we're going to see these particles that are rising from this volume emitter. And the speed that they have is coming from the emitter. Well, let's grab that emitter and make those move a lot faster. So let's say I go to the speed on that emitter and I make them or increase the along axis speed to 10. So now we can see how fast those particles are moving and when they eventually die. And maybe we also go and grab these particles then. I'm going to lower their lifespan so they don't live quite so long. And also I'm going to increase their radius so they're a little bit bigger. Because these could be smoke. If we were doing software renderable smoke, you'd create this kind of overlap between the particles. And so we can see how fast they're exiting the emitter. Well, if I want them to eventually slow down, because remember that the speed that they have is not a constant acceleration like a uniform field would be or a gravity field. They are given a velocity at frame 1 by the emitter, but then at that point on, they just continue to move in that direction because their conserve is at 1. Now, I could get those particles to slow down by lowering the conserve, but then that would completely change how they behave with fields. And objects in the real world do conserve momentum. So what I can do is select the particles and add a drag field. Drag fields by default will be created with attenuation on, but very often I turn off the attenuation, so my drag field just exists within the entire scene. If I now hit play, what we're going to see is these particles are going to slow down. And what I'm going to want to do is start increasing the magnitude of the drag field. Right now, the drag field's default magnitude is 0.05. If I give it a magnitude of 5, notice how quickly these particles slow down. Let's give it a magnitude of 1 and hit play. Give it a magnitude of maybe 0.2. And now you can notice how those particles slow down. So it's a braking force being applied to the particles. And by default, a drag field will slow particles down regardless of what direction they're moving in. But if you select a drag field, you will see that there are attributes called direction X, direction Y, and direction Z. And then an attribute called use direction, which by default is off. That being off means that by default, the directionality that the particles are moving in doesn't make a difference. It'll slow them down regardless. But if you turn use direction on and set direction Y to 1, what we'll see is that drag field is still working. It's slowing particles down that are moving in the Y direction. But if I set direction Y to 0 and direction X to 1 and hit play, notice that it's not slowing the particles down. It's only going to slow particles down if they move in the X direction. So it's just an added level of control you have with drag fields to control how they brake or apply a braking force to your particles. And so another example of something like a drag field is if I jump into, let's say, I'm going to grab a scene that has some particles that slow down. So in this scene, for example, I'm going to need to play blast this just for performance reasons. But I have a couple smokestacks that are emitting some smoke, and in the first few frames, the smoke is coming out very, very slowly. And then the speed on the emitter rises so that those cylindrical objects, those revolved surfaces, start emitting smoke at a much higher rate. And then at that point, we'll see that the smoke slows down very quickly. Over the course of about 10 units, it loses most of its energy. And then I also have a turbulence field in there that causes the smoke to dissipate into the scene. So if I look in the outliner, what I can see is that I have a drag field and a turbulence field. And those are the only fields that I have in the scene. And again, as far as the speed that the particles have at birth, it's just coming from the actual emitter that's emitting that smoke into the scene. So drag fields can be used either with attenuation at 0, so that's in the entire scene. You can use attenuation. You can use all of the volume shapes and settings and so forth. So we'll give this a couple more seconds to buffer in just so we can see it from the side. And so we have a lot of sprites in here, which is why it's taking a couple frames per second for that to load in. And so now we can stop the play blast, which is going to load it into FCheck. And so we can see that once those particles, the speed rises up. And so now, in the first it looks jumpy just because the sprites are loading, which is normal behavior. But if I sort of scrub through here, notice how fast the smoke is exiting those columns at birth and then how quickly it slows down. And so it slows down, but it still has a turbulence on it, so the turbulence becomes more pronounced once they lose the speed given to them from the exhaust. And so when we hit play in here, we can see what I'm talking about. So that pretty much explains the basics of and uses of drag fields. What I'm going to open now is the particle grid again so that we can talk about the radial field. And so with the particle grid, I'm going to select it, create a radial field, and go to the creation dialog box and hit reset. And in the creation dialog box, we have magnitude and attenuation. And then we have use max distance and the volume settings. As far as the default settings, we can see that the magnitude is positive. It has an attenuation, which is at a value of 1. Max distance is on with a value of 20 units. So what I'm going to do is hit create. And then it's, by the way, its unique attribute is called radial type, which has to do with attenuation. So I'm going to hit create, and our radial field will be at the origin, and I'll hit play. And so we can see that a radial field pushes things away by default. And so if I move the radial field below the particles, we'll get this. If I move the radial field to the right, we'll get this. And we can see based on the max distance that it's only pushing particles away that are within 20 units, because the max distance is set to 20. So moving the radial field back up here, let's say I turn off the use max distance so that it's now at a value, use max distance is off, and I hit play. It's just going to affect the particles forever. But instead of having a positive magnitude, let's give it a negative magnitude, -2, and hit play. And we're going to see this. And so radial fields can be positive as well as negative. If I go in and turn the use max distance back on and give it a value of maybe 50 units, by turning the max distance back on, the attenuation, which is on, will become more noticeable. And with our negative magnitude, we will now see this result, which is going to be a little bit more interesting due to the fact that the intensity of the field fades with distance. So positive effect versus a negative effect. So a radial field clearly can be used for doing anything from an explosion where you need just a outward force to controlling where in the scene, for example, particles move. By having a negative radial field, particles can become attracted to a certain part of your scene, or this radial field could be apparented to objects in the scene. So what we're going to look at as far as a couple examples is, let's say that I go and open a scene that we previously had where we did the ground fog. Well, in here I actually have a sphere which is going to move through that particle grid, or actually I created that using the particle tool. But right now we'll see that there is a field in here that I'm going to turn off. So I'm going to turn off this radial field. And when I hit play, what we'll see is that this sphere is a collision object. So that when I hit play, notice that once we hit frame 100, it moves through the particles. And those particles then, you can see it leaves sort of an empty void in its wake. So this surface, if I go to the attribute editor and go to the geoconnector node, has resilience at 0 and friction at 0. So then when that surface hits the particles, they don't bounce off of it, they just slide along it and move out of the way. But in the real world, if you think about something like this occurring, let's say that, if you think of the opening for Star Trek Voyager, where the ship moves through sort of a particle cloud or gas cloud, similar to something like this, you'll notice that behind it, you're going to get kind of a vacuum, because as an object moves through gas or mist or smoke, the space behind it is going to have a vacuum, which is going to suck particles in. And we are not getting anything like that when we hit play. So to create something like that, what I have is I have parented a radial field to this sphere. And the radial field is sitting towards the back of the sphere, and it has a negative magnitude. So the magnitude is at -12, the attenuation is on, and the max distance is set to about 10 units. So if I now connect that radial field to the particles again, so select the particle object, select the radial field, and I hit play, what we will now see is that we will get that kind of effect, because as the sphere passes through those particles, that radial field is going to suck them back in. And so now we get something that is really a much more natural result by simply using a negative radial field. Now, we also could use a field which is called an air field with a negative value to create a similar result. But at this point, for this effect, you can see that this really gave us results that were satisfactory to create that kind of vacuum. Another example where radial fields can be very useful as far as because of their basic behavior of pushing things away or attracting them is doing particle-particle collisions. Something that Maya cannot do by default is particles cannot collide with other particles, but there is a workaround. Let's say I go and create some particles where I'm just going to click with the particle tool, and I'm going to place some particles down here. Now, what I'm going to do with these particles after I've finished creating them is I'm going to put them into sphere mode and get them to be easier to see. So let's say they're spheres. I'll increase the radius a little bit, and I'll also give them a color so that they are all, let's say, green. So that now we can very easily see those. And let's increase the radius even more so that we can clearly see that some of them are intersecting. So some of these spheres are intersecting with other spheres. Well, what I basically want is I want to get them to avoid each other. I want to get these particles to be able to, when they come near other particles, get out of the way or bounce off of each other. Something that you can do with fields in Maya is fields, instead of being standalone objects where I select particles and create a radial field so that we get this result where it pushes them away, instead of having your field be independent, you can actually connect any field in Maya to a particle object so that each particle is emitting the field. And you can also do this with a rigid body so that the rigid body emits the field. And you can also do it so that vertices emit a field. The way that you can get points to emit a field is first you have to create the field like I just did, then select the field and shift select the particles or the points that you want to emit that field. I can then go to fields, use selected as source of field, and that's going to do what it sounds like. It now means that if I go to the outliner, our radial field has disappeared, because if I open up my particle object, the radial field is now a child of the particle object. But what will happen if I hit play is it still seems to be doing the same thing. The radial field is pushing the particles away from what seems to be the location of the radial field. Well, what's actually happening is, based on the default settings, the radial field is not going to be emitted from each particle. It's going to be emitted from the center of all of the particles combined. And so what you will see is all fields have an attribute which is called apply per vertex. And by default, that attribute is off. If you turn apply per vertex on when a field is being emitted from a particle object, so I'm going to turn that on right now, what that will mean is now each particle is a field. So if I now hit play, what's going to happen is we're still going to get this result where they seem to be getting blown away. Well, that's because the radial field attributes have a very high max distance. Well, let's say I go to the max distance and enter a small value of like 2 units. So the magnitude is at 5, attenuation is at 1, but the max distance is very small. And now I'll hit play. And let's increase our playback range to about 1,000 frames. And what we are now seeing is what looks like particle-particle collision. It's a very convincing way to achieve something which Maya cannot do by default. Because now that each particle is a radial field, based on their max distance, they can bounce off of each other. And so by setting, let's say, lowering the attenuation and increasing the magnitude, we'll get a harsher bounce when they come near each other. And so I am allowed to then also take these particles, maybe connect gravity to them, and also maybe I'll create a surface in here, like a ground plane, which can be a collision object. So I'll say make collide, and give it a little bit of resilience and a little bit of friction. And then I'll connect those particles so that they can collide with that ground plane. And now when I hit play, what we'll see is the particles will fall with gravity, but also they will collide with that surface and try to avoid each other. And so now we're getting a result that kind of looks like billiard balls as far as the result. So when you're doing something, let's say like a swarm of bees, or a school of fish, or a flock of birds, using particles where you're going to use the instancer to replace those particles with geometry, this is a very useful way to make sure that those fish or insects or whatever avoid each other, so that when they get near each other, they don't go right through each other, by just doing this radial field technique where they automatically are going to give this behavior. So instead of going and having this plane in here, I could also go and still take the particle object and maybe put a radial field that's negative, that's attracting those particles. Maybe give it a -1 field, and let me get rid of the gravity field. So we can see that they're going to become attracted to that radial field. But the thing is due to the radial field that they're actually emitting, they avoid each other. So now my particles are avoiding each other while at the same time being attracted to a radial field that I've created in the scene. So if I go to frame 1 and set a keyframe on my radial field, hit play for a few frames, and then maybe gradually start to move that radial field somewhere else in the scene, and hit play, we'll just see that as that radial field starts to move, those particles will follow it. So it's kind of like a little swarm of gnats right now, or a little swarm of insects that are avoiding each other but being attracted to that radial field. So by putting that radial field on a motion path, I can control where in the scene they move. And maybe I'll increase the max distance on that so that it affects particles greater or further into the scene. So at this point, now that we've talked about radial fields, again, we'll make a new scene and move on. So next scene that I'm going to open up is going to give us an example of the Newton field. The Newton field is something that people tend to think is related directly to the radial field. But actually it is very unique in the sense that it's related to mass. And so what I'm looking at here is a single particle object. And this particle object, I've gone in component mode and made a couple changes to some of the particles. Specifically on the particle object, I added radius pp, and then I also added a RGB pp, so that in the component editor I can make some of the particles bigger. So basically this yellow particle, I made it bigger, but I also increased its mass. And then the blue particles, I made them a little bigger than the green ones, and their mass is also larger. So that if I go in component mode and select some of these particles, what you will see if you go into the component editor is that all particles by default have a mass of 1. And so we can see in the particle tab, all the selected particles that I have right now have a mass of 1. But if I select one of these blue particles, this one has a mass of 11. And if I select this yellow particle, it has a mass of 50. What the Newton field will do is, what I've done in here is it's very similar to what we did with the radial field, where I have each one of these particles emitting a Newton field. And when you do that, what the Newton field does is it creates an attraction between the particles based on their mass. So it's based on Newton's universal law of gravitation that objects attract each other based on their mass. So when I hit play, if you look in here, what we're seeing is, notice that the yellow one is moving because it is related to the mass of all the small particles, but at the same time, all of the particles are basically in orbit around the yellow one. And so you can see how the blue ones are in orbit around the yellow one, and then the green ones as well. So its basic use is for doing anything from something like a recreation of like a astronomical type event, or you can be using it to create relationships between things like swarms of insects and whatnot, where you can write expressions where, for example, if you wrote a creation expression where you grabbed a particle object and said that the particle shape dot mass equals rand, let's say 2, 5. Well, what this would mean if you wrote this as a creation expression would be that at birth each particle is given a random mass between 2 and 5. Well, if that particle object also has a Newton field connected to it, where each particle is emitting a Newton field, each particle would be attracted to other particles with a varying degree of attraction. So going out into Maya, just so we can sort of take a look at setting something like this up, if I make a new scene, or actually let's say we start with something like a particle grid. If I just have a regular particle grid and I connect a Newton field with default attributes, so I hit reset, you'll see we have magnitude and attenuation, we have max distance, but then the unique attribute for a Newton field is min distance. So not only do you have max distance, you also have min distance. Well, if I hit create with the default attributes, and I move this Newton field up above the particles and I hit play, it's going to look like a negative radial field. In the sense it's just attracting these particles to the location of the Newton field. And so if I increase its magnitude, let's say to 20, it'll just speed those particles up. So let's go back to frame 1, and we can see the effect we're getting. If I change the magnitude, though, so instead of being 20, the Newton field has a magnitude of negative 20, then it's going to push the particles away, like the default behavior of a radial field. So again, the unique behavior comes when you use the mass settings and have particles emit a Newton field, or even have rigid bodies emit a Newton field to get rigid bodies to orbit each other. So what I'm going to do for something like this is, let's say I select, or we create a particle grid that doesn't have quite so many particles, so it's easier to see what's happening. So I'll go to the particle tool, create a grid, and with the grid, I'm going to get these particles to be spheres. And then also, let me get these particles so that I can have one of them have a different color. So right now, for the particles, they're all going to be, let's say, green. But I want one of the particles to be red. And so I'm going to add a per particle RGB so that I can now go to the component editor. And in component mode, using the left button, I can go to particles, select an individual particle like I've just done, and then enter a value for its color in the component editor. So that now what we'll see is I have a single red particle in the lower left corner of this particle object. Then what I want to do is, right now, also notice if I select these particles, so I'm just going to select all of them and go to the component editor, and let me select those one more time, we will see that they all have a mass of 1. So all of them have the same mass. And if they all have the same mass, and I attach a Newton field to them, so select Newton, and then with the Newton field selected, I will shift select the particles and go to fields, use selected as source of field, and then for the radial field, or rather for the Newton field, make sure you turn on apply per vertex. So I'll turn that on. Now when I hit play, we will see this. We'll see how those particles are being attracted to the center. Well, the reason it's happening like this is because all of the particles have the exact same mass. And so the result that you get is it sort of averages all of them, and they all get attracted to the center of that particle group. But let's say I select that red particle and give it a very high mass. So I'm going to go into component mode, select that one particle, then go to the component editor and enter a mass. Right now it has a value of 1. Let's say we enter a value of 100. If we now hit play, what we're going to see is this. Notice the difference in the result, where now those particles are basically orbiting the red particle. Now things are moving very, very quickly right now because of the fact that our Newton field does have a high magnitude still. But I can go and select the Newton field, which has a magnitude of 5, and maybe give it a magnitude of 1 to mellow things out a little bit. And so now you can see that the green particles are all in orbit around the red particle. So to create one more example of how this works is, let's say we now create with the particle tool by sketching particles. I'm just going to create, let's say, 4 of them and hit enter. And for these particles, again, I'm going to get them to be spheres. I'll increase their radius a little bit. And again, I'm going to go in and give them a per object color. I'll make them blue, but then I'll select that one particle right there. I want it to be red, so I'll add a per particle RGB so that I can select that single particle, make it red in the component editor, and then I will go in, select this particle object, and add a Newton field. I will then select the particles, so select the Newton field first, shift select the particles, use selected as source of field, and now hit play. And we can see how these particles are doing the same thing. And if we hit play, we're eventually going to get this orbiting behavior. If I select the red one and give it a higher mass, so we're going to go into component mode, select the red one, component editor, let's give it a mass of 10. Go back to frame 1 and hit play. And we'll be able to see the increase in its bias. Now let's give it a mass, let's say, of 100. But one thing we have to do, which I think I forgot to do, is select the Newton field and turn on apply per vertex. So let me turn that on. And now when we hit play, you can see how the blue ones move right towards the red one because it has the highest mass. And now the blue particles will begin orbiting the red particle. So even if you're trying to create something like an atom which has electrons that are spinning around it for some sort of scientific visualization or whatever, you can see how this can be used to that kind of effect. And then the particles are going through each other. If we don't want them to, we can select the particles, connect a radial field, then select the radial field, shift select the particles, use selected as source of field, and then for the radial field, what I want to do is turn on apply per vertex and enter a small max distance with a high magnitude, say 25, so that now those particles will be able to bounce off of each other. And so I got to make sure in the dynamic relationships editor that the particle is connected to the radial field, which it is. And then I also need to check for the radial field that apply per vertex is on, and then I'm going to increase the max distance. I'm going to lower the attenuation to 0.5 and increase the magnitude and hit play. And now we can see that those particles are bouncing off of each other. And I can actually lower the max distance down to 2 and hit play again. It actually needs to be a little higher. And let's play this. And now we can see the result that we're getting. So the blue ones are orbiting the red ones, but the particles are bouncing off of each other. So that's the basics of a Newton field as far as the type of functionality that you can expect to get with it by incorporating mass. So it is a very unique field that has, as all the fields do, a wide range of applications. So at this point, new scene, and let's move on to the next field. So the next field that we're going to take a look at is going to be the air field, which is at the top of the list in the pull-down menu for fields. If I go to the dialog box for that, what we're going to see is that the air field has several more unique attributes than most of the fields. If I hit reset, the first thing that we'll notice in here is that there are 3 buttons at the top, which are preset buttons. And the air field is the only field that has these presets, or the idea of presets. And so what we see is wind, wake, and fan. You actually don't need to ever use these. All they do when you click these buttons is they change all of the attribute settings for all of the attributes below. So I'm just going to hit reset so that we can really focus just on what the attributes actually mean. An airfield is something that can be seen as being the spotlight equivalent of what a radial field is, with a few extra bonus attributes, in the sense that an airfield can have a spread value. But there is one thing about airfields that is very unique, in the fact that how its velocity, or the way that it's moving and rotating, can control or determine its magnitude or its effect on particles or rigid bodies. And so what we're going to want to do to understand this field is, if I first, let's say, open, let's start with this scene. What we'll see in here is that I have this cone, and parented to this cone is an airfield. And this airfield, if I go to the Show Manipulator tool, notice that all fields can actually have custom manipulators. So any field, if you hit the Show Manipulator tool, will show you these. And so for an airfield, we can see things like magnitude, attenuation, direction. I tend to avoid using these, but for an airfield, the spread is quite useful in allowing you to see where it's pointing into the scene. And this airfield is parented to this cone. So if I hit play in here, what we're going to see is that it's rotating, and then these particles start coming down. And then notice that as this sort of wall of particles is descending and that cone is rotating, it is causing an effect on the particles that is sort of showing you that it does have this kind of spread. idea as far as how it's affecting those particles. So if I select the air field that's in there, what we'll see with it is that it has your standard magnitude and attenuation and max distance settings, as well as apply per vertex, all of the standard volume settings. And then you'll see it does have a directionality. And so for this airfield right now, its directionality is set, but once you parent it to an object, it can become confusing as far as what the directionality actually means. And then what I'm going to do is, so that now we can see that spread idea being in there, is let's make a new scene, or actually let's open that particle grid that we've used before. With this particle grid, if I select it and create an airfield with all of the default settings, the airfield will pop up at the origin, and if I hit play, we can see how by default an airfield is pushing things up in the Y direction. And so at this point it seems like a uniform field with attenuation, or a gravity field with attenuation. But the thing to notice is with this airfield, first obviously it does have these direction attributes, direction X, Y, and Z. Right now direction X is set to a value of Y. So if I set direction, or direction is set to a value of Y, with Y being 1. So if I set direction X to 1 and Y to 0, and I hit play, we'll see the particles are going to move in the X direction. Also, right now, attenuation is on, so if I turn attenuation off, putting attenuation to 0 and hit play, we're going to get this kind of standard result. So in here, though, I'm going to turn attenuation back on, and then move focus to the spread attributes. The airfield has an attribute that you'll see towards the bottom of the channel box called enable spread, which is off by default. If I turn enable spread on, so I'll just enter a value of 1 there, now when I hit play, we see this. And so you can see that how this airfield is now going to behave more like a spotlight, in the sense it's only affecting particles on one side. And again, we can hit the show manipulator tool, and then in the show manipulator tool underneath the field, it's hard to see, but there's a little blue circle, and if I click that, it'll run us through some of the different things that can be modified using the manipulator, such as direction, speed, and so forth. Well, right now we're looking at the spread. The spread has a range from 0 to 1. A spread of 1 is a spread of 180 degrees. But if I start changing that, you can see that I can create a much narrower spread in here. So I can either use the spread attribute in the channel box or use the manipulator. If I now hit play, we're going to see this as far as how it's affecting the particles. So the spread attribute is relatively intuitive. And something to be aware of is if I now go and rotate the field, so let's say I rotate it a little bit and hit play, notice how the rotation has made a difference to what direction it's blowing the particles. And so the next attribute we then need to point out is this attribute called inherit rotation. Inherit rotation is on by default, and it basically means that if the airfield or its parent rotates, the rotation will affect how the field behaves. So right now it's on, but if I turn inherit rotation off, if I hit play, we're getting this result. But if I then rotate the field and hit play, notice how the rotation did not have any effect. And so going back to the previous scene where we had these particles coming down, we can see how the rotation of the field's parent is definitely affecting how those particles are being pushed. But if I go and select that airfield and turn off inherit rotation, so I put inherit rotation to 0 and I hit play, we'll see this. The rotation of that field's parent has absolutely no effect on how the field is affecting those particles. So you can see the direction Z is set to -1, and that's all that matters, meaning that it's more of a global effect as opposed to being local or relative to its parent. Then the next thing we want to see in here is, let's go back to the particle grid. So I'm going to get that back up here. Select the particles, create an airfield, and then for the airfield, hit play. So we're back to it moving up. I'm going to get this airfield so that it's pushing the particles in X again, and so that its spread is on with a spread of, let's say, 0.4. So now the particles are moving this way. So granted, if I also took this field and, let's say, just keyframed it moving, so let's say I move the field over here and set a key, move it over here, and then set another key, and hit play, we're going to get an effect, which at this point, let me just go and delete the keys that I just set. And I'm going to make a change to an attribute that's in here. Because what we probably expected to see is not what we're seeing right now. We were kind of expecting a wake behind the airfield, but all of a sudden it seems like it's pushing the particles in the opposite direction. That's because this airfield has an attribute called inherent velocity, which is on by default. So that this particle, or this airfield, has a magnitude of 4, a direction in x, which is this way to the right. And so it's going to push particles to the right, but at the same time, inherent velocity being on means that the velocity of the field also determines how it affects the particles. So if the field is moving to the left, it'll push the particles to the left while also pushing them to the right. So if I turn off inherent velocity, set that to 0, and I hit play, we will now get this wake that maybe we were expecting to get. So if we're doing something where we are trying to create a wake behind a boat, for example, you definitely can use an airfield with a spread. Just make sure you turn off the inherent velocity setting, for example, if you just want that spread to stay behind that field or behind the object. At the same time, I could go into the magnitude and set that magnitude, let's say, to -4 instead of +4. And when I hit play, notice how it attracts the particles instead of pushing them away. And so let's go in here and set maybe a -1 setting so it's not quite so strong of a result. Okay, so the next thing we want to take a look at then is, now that we've seen the inherent velocity has an effect, let's try and see a useful application of the inherent velocity setting. So what I'm going to do is, let's get rid of this airfield and create another one. This time I'm going to go and create a curve which I'm going to use as a motion path. So I'm going to create this curve that's moving through the particles. And then I'm going to create an airfield. So I'm going to select the particles, create air, and then with that airfield selected, I'm going to select the curve and then apply that as a motion path. Going to animate motion paths, attach to motion path. And then in here with that motion path setting, I'm going to set it, let's say, for 120 frames. Let's say 150 frames, it'll go along that curve. And I have follow on, meaning that the airfield is going to actually be rotated as it moves along that curve. And at this point, I'm going to hit attach. So if I hit play, what we're going to see now is I have a brand new airfield. And notice how these particles are getting this sort of strange behavior now. Well, what's happening is, since this is a new airfield, its inherent velocity attribute is on again. And notice how the direction that the field is moving in is changing how the particles behave. So if I wanted, let's say, the wake idea again, I just have to turn that inherent velocity attribute off. And now when I hit play, we're not going to get that result as far as the motion or the velocity causing an effect. So I could go in here and maybe say that the direction is -z, maybe give it a spread of 0.5 so that the spread is on, and if I hit play, we're going to end up having to sort of find the right direction. And so let me just go and set that to x and hit play, and let's actually set it to -x for the direction. And now you can see that we're getting a wake. And so notice that the wake, or the particles that are behind the airfield, are the ones that are being pushed back. And so we can see the rotations having an effect in here. If I turn inherent rotation to 0, when I hit play, the rotation of the airfield on that motion path is not going to have any effect at all. So you can see all the particles are being pushed to the left, as opposed to when I turn inherent rotation on, actually being pushed based on how that airfield is rotating. But now what I'm going to do is, I no longer want the wake idea. What I want to do is, let's say you have a situation where you have a character that's supposed to be walking through some ground fog, and you want the fog to be disturbed as the character's feet move past it. You could set the geometry of the character to be collision objects for the particles, but you more easily could just create airfields that are parented to the character's feet, and then rely on the inherent velocity attribute. And so what I mean by this is, let's say I go in and set the magnitude of this field to 0. So the actual magnitude setting is off. When I hit play, the field has no effect at all anymore. But now what I'm going to do is turn inherent velocity on. So the inherent velocity attribute does not go from 0 to 1. I can have it a value of 1, a value of 10, or whatever. The higher the number, the greater the transfer of velocity will be from the field to the particle's motion. So if I now hit play, we'll see this, in the sense that the particles are being moved based on that field. But I'm going to lower the max distance maybe to a value of 5 units now. And so hopefully you can see that the particles are being pushed based on the direction that that field is moving. It's no longer awake. It's no longer just on one side of the field. It's on both sides. And so it's really based on that field's motion. And so if I went in here, if we just let this play a little bit longer, okay, we'll see that the particles are not all going in the same direction. So if I put inherent velocity to a value of 5, now you'll see it's just those particles are getting pushed or getting a lot higher percentage of motion or a higher speed based on that airfield. So putting the inherent velocity, let's say, back to 1, there's an attribute that's related to inherent velocity called speed. The speed attribute determines how quickly the particles match the velocity of the field. And so if I set speed to 0 and I hit play, the inherent velocity attribute isn't doing anything anymore. But if I put speed to a value of 0.5, we'll see that the particles speed up, but it takes them a little longer to catch up with the speed of the airfield. But if I put the speed to a value of 1, now their speed increases a little bit quicker. And so we can make it more dramatic by increasing the inherent velocity attribute to 5. So this is with a speed of 1. And then let's put the speed to 0.2 and hit play. And we'll see how they move a little bit slower. So it's by balancing the speed attribute with the inherent velocity attribute that you get that result. And then also related is the component only attribute. When component only is off, which is the default value, the particles, as far as their motion, if that airfield stops, and so let's go and wait until it sort of gets to the end of the motion path, what you'll see is that the particles get sort of a slowdown. And so let's put the speed back to 1, the inherent velocity back on, and we'll hit play again. And so when the airfield slows down, it also creates a slowdown in the particles that are near the airfield. But if I turn component only on, the field's motion will only cause particles to move faster. It will not apply any kind of braking force to the particles. So if we now hit play, what we'll see is when the airfield slows down and stops, there is no slowdown at all as far as those particles that are near that airfield. So let's put component only off, and let's take these particles and lower their conserve to about 0.8. And then let's grab the airfield again and hit play. And so we can see, again, an example of the effect. So that when this airfield gets to the end of the motion path, we can see that that airfield is not moving anymore, and therefore the particles are not affected by it, even though those particles are within the max distance. But if I go back in here, let's say we increase the inherent velocity to 10 and hit play, we'll see what happens. Because the conserve being less than 1, they eventually slow down. But at the same time, they are only affected when the airfield is moving. So we can see my magnitude is at 0 right now. The magnitude does not have any value whatsoever. So an example of where this is useful, let's say we take a look at this scene, where I have an airfield that has inherent velocity on, and that airfield is parented to a joint. And then that airfield is connected to a soft body plane. If I hit play, we can see the result that it's having on that surface. Is that since the directionality of movement of the airfield affects its magnitude, we can see that the ripples that are created in the geometry move in the correct direction based on what direction the airfield is moving in. And so if you have a finger that needs to sort of move through some liquid, or that needs to touch a soft piece of cloth or whatever, it's something that can calculate very quickly and create very natural results without having heavier computation times and more complex setups that would be required if you tried to do the same thing by using geometry. So the next thing that we can see as being a useful example is we've talked about Newton fields and radial fields and how to get those fields to be emitted from objects, being emitted from particles or geometry. So what I'm going to open up is a scene where we have a soft body piece of geometry down on the bottom. Let's say this is water. And I have a plane, which is, if I switch to a different camera, what I have in here is I have this plane up here which is emitting particles that are falling down. And these particles, let's say they are meteors or whatever, those particles have airfields emitting from them. And the airfields have inherent velocity on. So what that means is that, if I had used radial fields emitting from those falling particles, and let's say I hit play so we can see that there are some particles falling. If I had used radial fields, the intensity would be the same for each particle. But if I use air fields, if some of the meteors are falling faster than other ones, the airfield, by using inherent velocity, would have a greater effect. So let's switch to a camera that's a little bit lower to the water. And when I hit play, I have a turbulence field on the water, which is why we're getting these waves and swells. But if we notice when those particles fall and hit the water surface, it's going to start to create ripples. And so the effect right now is rather small, because if I select the airfield, we can see that it's got, apply per vertex on, it's being emitted from those falling particles. But the inherent velocity is very low, it's at a value of 1. And the magnitude is at a value of 0. But if I take the inherent velocity and give it now a value, let's say, of 10, now all of a sudden we get a much greater impact. And so you can see that now when those particles hit the water surface, we can really notice what's happening. And so all of the reaction that we're getting in this soft body piece of geometry is based on those particles that are falling and hitting it. So these ripples that are being created and these waves and swells are all originating from the location where the particles hit the surface. And as far as the degree or the impact that they have, I can go and change the inherent velocity. So if I don't want the swells to be so big, I can set the inherent velocity maybe to a value of 5. And now when I hit play, we'll still get a result, it just won't be quite as dramatic. And so now we can see this one close by, how it created that dent and then the ripple that will move through the soft body geometry. So again, another example of airfields. So for the turbulence field, which is the next one we're going to talk about, the first thing that I'll do is start with a particle grid. And so let me grab that grid real quick and select the particles and go to the creation dialog box. We've already used turbulence fields or seen them used in a couple different examples, so you should already have a pretty good idea what they do. It basically creates irregularities or noise within the scene, which can affect your particles or rigid bodies. And if we look in the creation dialog box, what we will see is, if I hit reset, we have magnitude and attenuation as well as max distance and all the volume settings. Default magnitude is 5 and the default attenuation is 1, so the attenuation is on by default. And then we have some unique attributes, specifically frequency, phase, noise, and an attribute that will be available once we create the field, which is called interpolation type. So what I'm going to do in here is, leaving everything at default settings, and again attenuation is on, I'm going to hit create. And if I hit play, we're going to see what's going to happen to these particles. And so with this turbulence, all the particles are kind of going to go in different directions. But it's kind of hard to really understand how that turbulence exists in world space by just looking at what the particles are doing right now. We do know that max distance is off and that attenuation is on. But if I turn max distance on, and let's say set a value for the max distance of about 15 units, if I hit play, as you'd expect, the particles that are near the turbulence field will get the greater effect. And with a turbulence of 1, it's not really showing much a very noticeable fall off, and so maybe we'll try an attenuation of, let's say, 3. And now when I hit play, you can see that it's just the particles near the turbulence field. Let's then try an attenuation of 2, and then we can see what looks like more of a obvious fall off from the location of the turbulence field to what the max distance setting is. So obviously this turbulence field could be parented to objects or animated moving around, so that if you had, let's say, a rocket that was flying through some smoke or some clouds, you wouldn't necessarily want those clouds to be behaving in a turbulent fashion. Maybe they're kind of at rest, but then when the rocket flies by the clouds, you want them to get a turbulent behavior. And so something like that could really be accomplished by just going and having a turbulence field that's parented. So if I go in here and move that turbulence field through that geometry, or through those particles, we'll be able to see that result in here. And maybe I'll go in and increase the magnitude, so that's a more obvious result that we get as it moves inside there. Now, when I play that, when we take a look at what's happening, we'll notice that there seems to be, some sort of linear breaks in how the turbulence field is affecting those particles. And that's something that has to do with the way turbulence behaves, in the sense that a turbulence field, while I've actually animated turbulence moving, the turbulence itself is not an animated field, or the noise inside the turbulence isn't animated. So if I animate the turbulence field moving, what's happening is the sort of noise pattern is moving with it. And so that's why we're getting those kind of linear breaks inside the particle object. Something that we can do to modify that is to cause what's called a phase shift in how the turbulence affects the particles. If I go in here and, let's say, animate one of the phase attributes that this field has, it has phase x, y, and z. I'm going to write an expression on the phase so that the phase z equals, let's say, time times 4. And if I go in here and then hit play, what we will see is that we're no longer really seeing those breaks. And let me lower the max distance. So maybe the max distance is only about, let's say, 7 units. And then when I hit play, we can see that turbulence pattern occur, but we're no longer getting these breaks inside there. So it's not really going to make sense based on how I just showed it, though, what's going on. What I'll need to do to make it a little bit more clear is I'm going to open a scene where I have, let's say, some tendrils of particles that are being emitted. And so if I hit play in here, what we'll see is I have a curve that's emitting some particles, and these particles are falling with gravity. And we'll see that we're just getting these tendrils off these two particle objects that are coming off the curve, a blue particle object and the green one. Well, what I'm going to do is select these particle objects and apply a turbulence field to them. And when I do that, for the turbulence field, I'm going to turn off attenuation and hit play. And now we see this. This should make it a little bit more clear what's going on with the turbulence field based on its default settings. In that, when we look at these tendrils that previously were just hanging with gravity, now they're kind of going in different directions. But if you take a look at this, you'll notice that those tendrils are not waving around. They are moving through the turbulence field, but the irregularities within the turbulence field are static. They are not moving. And so that's why if you animate a turbulence field moving, we can see something like what we saw on that grid of particles when I animated the turbulence moving through it. So if we take a look at the turbulence attributes that are unique, we just animated phase before, but before we now do that again, there's an attribute called frequency. The frequency attribute by default has a value of 1. The higher the value, the more frequent the irregularities are going to be in the noise or in the turbulence. So if I lower the frequency to a value of, let's say, 0.1, and I hit play, what we're going to see is that these tendrils are going to change direction less often than they previously were. We're going to get these smoother arcs inside these tendrils of particles. But if I raise the frequency now up, let's say, to 0.5, let's go back to frame 1 and hit play, what we will see is that now there are sort of more sudden changes of direction as far as how these tendrils are moving through space. So the higher the frequency, the more frequent the irregularities, but it doesn't necessarily mean that anything in here is moving as far as the field. Now you could animate the frequency, but the thing is that a very often thing that you might want is a constant frequency of irregularity. You just want the irregularities to be sort of morphing and transforming within the scene. And that's why we have phase. So you have 3 different types of phase, X, Y, and Z. And so, because this will cause a shift in the phase of the turbulence or in the phase of the noise table in a certain direction. So for most effects, like something like this, if we just want these tendrils to be waving around, we could just animate one of the phase directions. We wouldn't necessarily animate all 3. But if you were doing something like a water surface with a soft body, you may end up animating the phase in more than one direction to determine what direction you want the swells of the waves, let's say, to move in on an ocean surface. So I'm going to go in here to the phase. Let's say we grab phase Z. I'll right-click on it. I could set keys, but instead of doing that, what I want is I basically just want my phase in Z to increase with time. So it just gets bigger as time goes by. And so I'll write an expression that just says that the phase equals time. And just so that you can see more clearly what I wrote, if I bring that into Notepad, basically, if I say phase Z equals time, those tendrils are going to start waving around. If I said that they equal time times 10, they'll wave around faster. So leaving the expression like this, if I hit create and hit play, what you will now notice is that those waves are no longer static. They're actually going to shift and move to the left and move to the right, and we're going to get what you might more intuitively think of as turbulent behavior. So to increase the performance a little bit, I'm just going to delete, let's say, one of these particle objects so that we only are left with one. And with this particle object, I'm also going to go to the emitter and lower the rate down. And this is just so that our performance increases. And so now we can see, if we look at these tendrils, notice how they're actually moving around. And so if I go in, let's say, and select the turbulence field again, I can still use the magnitude and I can still modify the frequency. So if I put the frequency back down to a value of 0.1, what we will see is that those tendrils are waving. It's just they have a much more subtle behavior as far as how often they change direction. But if I go in here and enter a frequency of 1, now what's going to happen is you'll notice those tendrils are going to move into this new sort of noise table, but change direction much more often. So this is independent of magnitude, in the sense that if I go back to having a low frequency, let's go back to frame 1 and hit play, if I increase the magnitude, what's going to happen, let's say right now is a value of 5. If I give it a value of 10, we're going to have a moving turbulence field, but it's just going to be more dramatic as far as the effect and how far the particles are pushed by the turbulence. If all I wanted was for them to wave around faster, but still have the same overall look, all I would need to do is have the phase increase faster. So instead of having phase Z equals time, I can modify the expression, say phase Z equals time times 5, to get those to wave around a little bit quicker. And so now you should be able to notice how they are changing direction. It's just as happening more frequently. So that's the basics of phase. There are other unique attributes in here. We have noise level, noise ratio, and interpolation type. Noise level is going to create what's called multiple lookups into the noise table to sort of increase the amount of subtle noise that you see. For an effect like this, you shouldn't really need to make any changes to your noise level or noise ratio. Noise level by default has a value of 0. If you give it a value of 1, it's going to do an additional lookup into the noise table and then average the lookups together. And so the noise ratio attribute only is going to have an effect if your noise level is greater than 0. And so this has to do with how the multiple lookups into the noise table are blended together. So for the noise level on something like this, if I set a noise level of, let's say, 3, and go back to frame 1 and hit play, it's not necessarily going to look dramatically different. Let's edit the phase so that they're moving around slowly again, and hit play so that we can take a look at what we're getting with a noise level of 3 versus having a noise level of 0, and hit play. So, I mean, you can notice a difference, but at the same time, it can be a little bit less intuitive than just modifying your magnitude and frequency. But when you're doing something like a soft body but that's being disturbed by a turbulence field, it can help to create additional subtle variations within the surface of the water by upping that noise level. Then you have an attribute called interpolation type. Interpolation type is something which, for, let's say, we open this scene where we had that uniform field affecting these particles. Well, if I go in and select the turbulence field that's in here, that's affecting them, I'm going to delete a couple of the expressions that are on it. I have an expression on the rotate y, so that that turbulence field rotates a y around. And I have an expression on the phase x as well as the phase z, so that the turbulence is moving diagonally through that particle grid. Well, I'm going to modify or get rid of the expression on phase x so that I only have an expression on phase z. And if I set the noise level to, let's say, a default of 0 and the interpolation type is at the default of linear, if you hit play, over time what you might notice is as the turbulence is moving in the z direction, you might start to see some sort of breaks within the z direction in the particles. And they're kind of starting to become more apparent, where we're kind of seeing these vertical lines through the particles. You can kind of reduce that by taking your turbulence field and changing its interpolation type from linear to quadratic. And so now when I hit play, it'll create a smoother interpolation within the noise table as far as how it grabs noise values. And you won't really notice those vertical lines. They won't be as apparent. And so now if we come in here, we won't see these sort of gaps appear like we would have before. It'll stay relatively uniform. Right now we're at frame 500, and so after 500 frames, things are still behaving all right. So with the basic attributes of turbulence understood as far as frequency, phase, and noise level, if we look at a couple other examples in here, one, if we look at the scene where we had those meteors falling, for example, let me grab that scene, and that is going to be in here somewhere. And what I'll do in here is, let me actually get rid of that. We can see that I have a plane which is emitting particles that are falling with gravity. I'm going to get rid of that. And I do have a turbulence field in here, which I'm also going to delete, so that when I hit play, nothing is happening with our water surface. But our water surface is a soft body, which means that it has particles which are representing the vertices. So I'm going to select those particles and add a turbulence field. The turbulence field has attenuation on, so I'm going to turn off the attenuation. Max distance is off as well. And if I hit play, what we will notice is automatically this will happen to that soft body. But we are not seeing waves that are moving through the surface. What's happening is that the particles are moving with that turbulence field, but they also have goal weights on them. So what's happening is they're moving up and then moving back down just because of the goal weight. If you actually want swells or waves to be moving through, what we would need to do is animate the phase. So if I want them to be moving in the z direction, I'll go to phase z and write that expression again, so that phase z equals time. Hit create, and now when I hit play, it'll be more evident that we have a moving water surface, in the sense of you can see how that turbulence is moving through there. So I can modify the frequency as well as the phase. So if I lower the frequency, let's say to a value of 0.2, and we go back to frame 1, notice that we're going to get less disturbance in that water surface. If I went in and increased how the phase had its expression so that it said phase z equals time times 5, they'd be moving through the surface quickly. If I increase the magnitude from a value of 5 to a value of 10, what that's going to do is basically increase the height as far as these swells that are moving through there. And so by balancing your magnitude with your frequency and phase that you could get the look that you want. And in here we can see that this camera is just assigned to that surface as a geometry constraint, so that the camera is actually rising and falling down as the surface does. So another example of a turbulence field, let's say with a soft body, is if I go into these scenes and grab, let's say, this one. What we're going to be looking at is just some geometry which has joints in it. So I can see that there are joints moving down those surfaces, and those joints have spline handles on them. And the spline handles, the curves for the IK spline handles, have been turned into soft bodies that have turbulence on them. And so now we can see that the way that these tentacle things are moving around is based on turbulence. So each one of these has its own turbulence field. So if we look in the scene, in the outliner, I have 5 turbulence fields in here, so that each one of these tentacles can have its own behavior, meaning they all have a different frequency, different phase animation, and so forth. Another example of using turbulence is, let's say we're doing some smoke. In this scene, what we're going to be looking at is just some sprite rendered smoke. So it's loading the sprites in. And now as we watch the smoke rise, I have a volume emitter at the bottom that's shooting the particles up. I have a gravity field that's lifting the particles, so the gravity is going up in Y. And then as far as how the smoke is dissipating into the scene, it's based on having turbulence. And so we can see that I can move in here and take a look at this sprite smoke. But then if I go into the scene, if I selected my turbulence field, again its phase is animated, it's got a low frequency and no attenuation. And so if I turn off my turbulence field and enter a magnitude of 0, what we're going to find is the smoke is just going to rise straight into the air. But if I put my magnitude, let's say, to a value of 10, now we're going to see that the smoke is going to start dissipating because of the turbulence. And then I can go and, let's say, give it a magnitude of about 5, and that'll be a little bit, just mellow it out a little bit. And put it down to a magnitude of 2, just so that the smoke rises and dissipates, but isn't too wild as far as its behavior. It depends what you're trying to do. But anyway, that's the basics of turbulence. So for the volume axis field, what I'm going to do is open a scene that gives an example of what it can be used for. It actually can be used for a wide range of things, but what I have here is, let's say, it's a rocket that's taking off. And we'll see that some particles are being emitted by a volume emitter that are being exhausted from the bottom of the rocket. They're hitting the ground, which is a collision object. They then slide along the ground, and actually I'm going to choose to play blast this instead. And so they slide along the ground as they hit it, and then as they slide along the ground, they then enter a volume axis field, which is a torus. Like any field in Maya that can have a volume shape associated with it, like a cube or a cone or a cylinder, a volume axis field will always have a volume associated with it. But what's unique about them is that they have a variety of ways they can behave. And so in a way, a volume axis field can behave like a vortex field or a turbulence field or a uniform field or a gravity field and so forth. And by being able to have multiple attributes to give it different behavior, it's as convenient so that instead of having to create more than one field, you can just have a volume axis field and have a lot of attributes in one place to edit. So what's happening in here is I have a torus volume axis field. And so when those particles slide along the ground and enter that torus, the torus has a sort of a vortex-type spinning force inside it, which causes the smoke to curl as it enters the torus. So this is something that you would not be able to do if you created a vortex field and gave it a torus shape, because the vortex field can only have a single axis. But in this case, we have sort of a circular axis for those particles to move inside. And so one example of a volume axis field. So we can see, if you'll notice, it's a little bit hard to see, but there are arrows inside this torus that are sort of showing this spinning shape or this curved arc. And so we can see that as the exhaust hits the ground and enters it, notice how it curls up. And so this is something that also could be used to do mushroom clouds, for example. And so if I open a scene with something similar to that, I'm just going to grab, let's say, this one right here. And what we'll see is that I've got an emitter, which is a cylindrical emitter that's going to be emitting particles moving up. And then those particles are going to exist inside a cylindrical field, which is a gravity field that's moving, pushing them up. But then once they get towards the top of that gravity field, they hit this uniform field, which has a cube shape, which keeps them from moving any higher than the top of this torus. And this torus is a volume axis field. And again, we can see these curved lines showing us how that field or force exists within that shape. So if we hit play, we'll be able to see that the particles move up, hit the uniform field so that they stop, then they start to spread out. And then once they enter that torus, we'll be able to see how they sort of will move with those arrows so that they come down, similar to what you would expect in something like a mushroom cloud. And so they're going to continue to move down. And these particles have a very low conserve, which is why they are moving with that field as opposed to being hit by that circular force and being thrown to the side. So to understand some of the basic attributes that these fields have, I'm going to open a, well, first let's make a new scene and open a particle grid. And we'll start with that. In a particle grid, if I select the particles and go to the Fields pull-down menu and go to Volume Axis, and then go to the Creation dialog box and hit Reset, you'll see that there are a lot more attributes on a volume axis field than most fields have because of the fact that it can do so many different things. You will have your default magnitude and attenuation as well as max distance. And then you will have your default volume shape settings. So you'll see that it says volume shape, cube, sphere, cylinder, cone, and torus. But then underneath that we have volume offset, which is also going to be standard amongst all the fields. And then we move a step below, and all of these attributes down here are all unique to the volume axis field. And some of them are very similar to the way volume emitters work. So you'll see that we have a long axis, a round axis, away from center, away from axis. So instead of determining particle emission, they have to do with how the field or the force inside the volume, what direction it's moving in. And so if I hit create with the default settings, we can see that we get a cube, and then the field is only going to be inside that cube. And by default, if we look at the attributes, magnitude is on, attenuation is off. And then if we look down at these attributes, we'll see that away from center has a value of 1. And then all of the other attributes in here have values of 0. So a long axis, a round axis, directional speed are all at 0. So if I hit play, we'll get this. The particles are being pushed away from the center. So if I put away from center to 0, and then turn on a round axis and give a round axis a value of 1, and now I hit play, we'll get a spinning field, like a vortex field, because it's now moving around this axis. So notice, if we look at this field, that it gives you arrows. So if I go to away from center, we get arrows pointing out. If I turn that to a value of 0 and turn off, let's say, a round axis, but then turn on a long axis, we'll get an arrow pointing up, showing us that the particles would move along that axis. If I then turn on attenuation, so we'll give attenuation a value of 1, as you'd expect, we'll see this. The field is strongest at the center and weakest at the edges. But volume axis fields have an attribute called invert attenuation, which is a Boolean. By default, it's off. If I turn that on, what we're going to see is this. Notice that the field is strongest not at the center, but at the edges of that volume. So if I went and turned off a long axis and turned a round axis back on, what we're going to see now is the particles are going to spin, if I increase the attenuation some more, are actually spinning more at the edges than they are at the center. So all of these attributes can be straightforward. We then have an attribute called directional speed. As well as the particles being spun, I could have the particles move on the x-axis. It's kind of like a uniform field. If I turn on directional speed, so I'll give that a value of 1, underneath directional speed we have direction x, direction y, and direction z. So if I give direction x a value of 1 and direction y and z values of 0, we now will get this. So the particles are spinning and also moving in the x-axis. So we now have something like a vortex field and a uniform field. And so they, with the combination of these different controls, it can be more intuitive than creating multiple fields. And then also we have a whole bunch of turbulence settings. If I turn, let's say, the turbulence on, give that a value of 1, and hit play, we now have something that's behaving like a turbulence field, a vortex field, and a uniform field. So I'm going to open up another scene instead of a grid, and this time we're going to look at a scene where I have an emitter, which is just emitting some particles. It's a surface, a NURBS plane that's emitting particles. And these particles are just popping up in the shape of a circle. And I already have a cylindrical volume axis field connected to them. But all of the magnitude values are at 0. So if I turned on, let's say, away from center, what we will see is that those particles, and let's go in here, and actually let's turn on away from axis. so we can see the arrows that pop up. Let's move the field so the arrows are a little bit clearer to see. If I hit play, we'll see what happens. Now these particles have a conserve of 0 right now, and so that's why they're not going to rush outside of that volume. By having a conserve of 0, they're just going to do what the field tells them to. If I then go in and turn on a round axis, give that a value of 1, now we're going to notice that they're going to be spinning. So if I give a round axis a value of 2, now they're going to spin faster. If I turn on invert attenuation and then increase the attenuation setting, now we can see that they are clearly spinning faster on the outside and slower on the inside. But if we want to look at the turbulence settings, let's turn off invert attenuation and mellow out our around axis. So we now just have these spinning particles. So we can see how those are rotating. I'm going to go to the turbulence settings, and where it says turbulence, I'm going to enter a value of 1. When I hit enter, we're going to see that we do get turbulence inside here, but it is a static turbulence. Well, underneath the turbulence, we have something called turbulence speed, then we have turbulence frequency, and then we have turbulence offset, and an attribute called detail turbulence. We already know what frequency and offset do, as they have the same function as a regular turbulence field does. But what's unique is that we have an attribute called speed and an attribute called detail turbulence. Well, if I go in here and let's say we hit play, and I'm going to mellow out the attenuation. Again, we are seeing that this turbulence is static. So if I lower the frequency, right now the frequency is at 1. I'll put it to a value of 0.1 and hit play. Now we can see that these particles are all being pushed in the same direction, but since the turbulence is not moving, we're not seeing any kind of moving effect. So I could then go to the turbulence offset and write an expression so that I can say that the offset in z equals time. Hit create, and we're going to get something similar to what we saw with the regular turbulence field, in the sense that the turbulence is now moving. So you can see the particles are not always going in the same direction. So they started being pushed to the left, but now they're being pushed to the right. And so as time goes by, you'll see that the turbulence is actually moving. If I increase the turbulence magnitude by giving turbulence a magnitude, let's say, of 3, and I hit play, we're just going to see how that directionality is changing. But if I want it to change faster, I'll go into the turbulence offset expression and say that the offset in z equals time times 5. Hit enter, and then now you can notice how we have moving turbulence inside the volume. So this is something that's going to give us, a very natural, smooth change in direction in the turbulence. But instead of using the turbulence offset, what you can do is I'll enter that back to its default value so that now the turbulence is not moving, and use the turbulence speed attribute. If you turn on the turbulence speed, that'll keep you from having to keyframe the turbulence offset. So that if I now increase, so my offset is not animated, I'm going to go to turbulence speed and enter a value of 1 and hit play. And now we see this. And so notice that the turbulence is moving without actually animating any of the turbulence attributes or any of the turbulence settings. And so turbulence speed by default will give you this kind of behavior or movement within that volume axis field. So you then also have an attribute called detail turbulence, which you've increased that will basically add noise on top of the noise. This will become more noticeable if we move on to, let's say, another attribute or another scene file where I've got, let's say, this whirlpool. In this whirlpool, we see that these particles are spinning and then also getting sucked down. And the reason that they're behaving this way is because the field that I'm using now is a volume axis field, which has a shape of a cone. And for the cone shape, I have a round axis set to -1, so they're spinning clockwise. And then I also have a long axis set to -5. If you wanted to do what we're looking at right now without a volume axis field, we would have needed a vortex field, a gravity field to pull the particles down, and then also maybe a negative radial field to get them to be attracted to a point. So instead of doing that, I can have this cone. And when you use a long axis with a cone shape, the axis is not going to be just in one direction. If you look at the arrows, you can see that it's pushing them towards the sort of pole or point of the cone. And so by combining a round axis with a long axis, we're getting this kind of whirlpool effect. And then if I go in here and increase maybe the turbulence, so I'll enter a turbulence value of 0.5 and a turbulence speed of 0.5, we will now see that we're going to have turbulence in here as well as our vortex behavior. And then that turbulence is automatically animated and moving because of the fact that we have this unique turbulence speed attribute. And so it really can be used in an intuitive fashion. Another example seen is this, let's say, aurora type effect, where if we look in here, I have these particles that are emitted that are moving up, or moving in the z direction. They are existing inside a volume axis field, which is a cube. And then in that cube, we'll see I have direction speed on going in the negative z direction, which is what causing these particles to move to the right. But then I also have turbulence on, and I have turbulence speed on. And notice that these particles, as far as the turbulence speed, are changing direction, and it's very smooth. Well, what I can do is increase my detail turbulence. Let's give that a value of 1. And now notice that there is a much more sporadic irregularity within the turbulence. So they're still kind of moving generally in the negative z direction, but at the same time that detailed turbulence gives us noise on top of the noise. So we get this sort of waving pattern, but at the same time there's a randomness to it, which really has a very organic look to it. So you can see if you're trying to do some sort of weird, nebulous space phenomenon or whatever, you could use this and very quickly get results that are unique and different to the regular turbulence field as far as the type of behavior we're getting inside our particles. And so that's pretty much the time we have to talk about volume axis fields. But hopefully you can see that they are very unique and how quickly I could go in and decide, I need these particles to also be spinning. So I'll just go to a round axis, give that a value of 1, and now we can see we have a vortex behavior in here as well, while we also have that turbulence with the detailed turbulence on. If I decide I also need these particles to be moving not only a little bit in z, but also in negative y, I can go to a long axis and give that a value of negative 1. And now we're going to see these particles are going to move in negative y, while they are also still spinning and also behaving with turbulence, all by using a single field. So that's the volume axis field, and that's pretty much the time we have to talk about all the fields in Maya. And there you go.